Okay. Thank you to be here. As I told you before, it's a little bit strange to be in a room totally alone. But anyway, the lecture nevertheless must be held in any case. Last time we concluded starting with an exercise, but just starting. This means you can find the lecture, of course, in my uh, YouTube channel. I don't know if I shared the link, probably yes. But in any case, I will do also the next days. Please sometime remember me if I forget to do something which I told you here. It could happen because it's not so easy also for me to organize or to hold all lecture alone in the sense without any official assistance in the sense or help. Okay, let me switch on the lateral camera. Do you remember last time we, yeah, analyzed a system of the second order, a linear system of the second order. The system was, just to remember, this one, a concrete system, a circuit, an RLC circuit, a little bit particular because probably in electrotechnic you analyze in a series LR circuit, and here a little bit the topology of the circuit is a little bit different. But anyway, the concept, let me say the principle which is necessary to analyze mathematically the system here is the same. No? You remember the Kirchhoff law, first Kirchhoff law, second Kirchhoff law, and so on. You remember I introduced also the concept of the switch. I will repeat now um, in our lecture the concept of the switch, because with the example which we conclude last time, which basically is not different. I mean, the mathematical expression could be uh, basically the can represent exactly this circuit. Let me see again this explanation. Let me show you again this explanation. Why is basically, yeah, it's here. Exactly in the first page. I built, if you look on the YouTube, the mathematical model. At the end, we have an equation of a second order. Therefore, I told you at the beginning, we analyzed this system here, which is in a system with two states. And look, if I consider this particular choice, R equal 1, L C equal 1, C equal 1, L equal 1, we have exactly this expression, which is basically the system which I would like to consider now, in which u of t is t multiplied sigma. We analyzed here last time. We concluded this system here, the analysis of the system here, which came from this, just analyzing the free answer. Free answer, do you remember? 0 as u of t, and I activate the initial conditions. We will see in the next lecture the meaning of this zero, no? The meaning of this zero. We will start a little bit also today. It seems to be straight. The meaning of, the meaning of this zero here, the initial condition. But let me go ahead a little bit slowly, because also the meaning of this is a little bit, let me say, complicated. I will start a little bit today to introduce the meaning of the zero. This sentence. I don't know if you heard about 0 minus 0 plus. Short before 0 and short after 0. What is the meaning? You remember I introduced last time the switch? The switch means, now I will characterize again this concept here. The switch means that at time 0, I switch on. This means it makes sense to analyze what is the let me say, the initial condition at time 0 minus. 0 minus means short before. And what happens between 0 minus and 0 plus? Because in this transient, it could be that something interesting it happens. But this will be done a little bit later. Now, let me consider the system here, not so in depth. This is the input. This is the, let me say, formulation of the our problem. Is the fourth answer or the fourth problem in our circuit, in which I am considering as an input T multiplies sigma. Let me tell you about sigma a little bit again, even though we will see a little bit later in detail. What is this sigma? This sigma, as I told you now, can represent this switching element, which states exactly what happens, let me say, at time 0. It's not here in this slide, because, as I told you, this analysis is a little bit more complicated. I need to introduce, let me say, different concepts. But let me nevertheless start. The sigma here as a switch is a function, which is 1 if t larger or equal 0. 0 if otherwise. No? This means this function here can be represented in this form. I don't know if I have another color. I don't have the shade. 0. Let me say 1. It's not a continuous function, therefore switch, step. And of course, we can see that at time 0, here we have 0 plus, and here we have 0 minus, in accordance with what I told you until now. And of course, we can understand that in such a situation, makes sense to analyze also in the circuit, also in the dynamical system which we are represented, what happens between 0 minus and 0 plus. This I will do a little bit later. At this moment, if you think about this formulation, I didn't distinguish. I didn't consider this 0 minus as 0 plus. Assuming that UC force at 0 minus equals UC force at 0 plus equals 0. And also here, the derivative of UC force at 0 minus equals the derivative of C force at 0 plus equals 0. Even though we have an input which is a little bit particular with this sigma. I mean, from the engineering point of view, must be nevertheless justified, must be considered what happens between 0 minus and 0 plus in such a form, in the presence of such input in this sense. But let me assume that you C force at 0 minus equals UC force at 0 plus equals 0, and UC force dot 0 minus equals UC force dot at 0 plus equals 0. But of course, this should be in the future considered, but slowly, because now we are analyzing more the dynamics. I am refreshing the differential equations, but in the context of free and forced answer. This problem we don't have in this formulation here, and the free answer, because this is 0. This is basically 0. We don't have any, let me say, switching situation. If I put here 0, this means I am starting analyzing the condition that this switch is on this position here. Remember, this is short circuit. Of course, we don't have this kind of problem, or at least in this situation when at t equals 0, I am in this condition, at least for this problem here, no? For this problem. Yeah, okay. Let me now go ahead. I am thinking if I forgot to say something, but I don't think so. I don't think so. Of course, it could be that should be clarified a little bit the meaning again of the free answer, because of course the free answer is more abstract than the force. The force is quite clear. I mean, I don't have initial, I don't consider the initial condition on the capacitor, the energy which I have, the voltage which I have, also the same situation for the inductance. And at time 0, I switch. I start feeding the circuit. This is physically quite clear. The free answer a little bit strange, because if you consider the definition, which the switch is this position here, and if I consider here an initial condition, the initial condition cannot be present with or without this position here, because if you think about physically, we cannot maintain this, at least in this configuration, the voltage here independently. I mean, without the input, no? Because of the presence of the resistance. This means it's really something a little bit more abstract. But think about, as I told you at the beginning, so we clarify a little bit again the concept of the free answer, that we are considering the initial condition, voltage here, the current here, or energy, do you remember, as a possible cause, as a possible input, but internal input in the sense. This means as if I put here 0, again, UC minus equal UC plus equal 1, UC derivative 0 minus equal UC derivative U plus equal 0. And in an abstract form, again, between 0 minus and 0 plus, no changes. Here is more abstract to be understood. It's more abstract to be understood. But anyway, remain a little bit on this concept here. We'll come back more in depth when I try to analyze a little bit deeper this system here. Okay. Do you remember? I told many times the U forced consists of a structure will reflect the free answer with different K1 and K2 because we have different initial condition. Again, forget at this moment 0 plus 0 minus. Assuming that no the conditions are the same at time 0 minus 0 plus 0 0 as for the free answer. Plus the function which must be calculated, we takes into account the contribution of the input now. Because basically, do you remember, I told you many times, basically, the problem of the force consists of, yeah, if you look at this equation, roughly speaking, we can see that we have a free answer structure here, plus, let me say plus, if you put this on the other part, plus in the algebraic sense, an input. This means I can assume, and I demonstrated too that this assumption is totally justified, that the structure of the UC force consists basically on a part which is quite similar, the same, except for the constant as the solution of the free, plus something which I have to calculate. Now, K1 and K2 can be calculated later when I have this one, because I have the initial conditions. Why that? Because the initial conditions influences also this one, even though it's 0. I don't know if you remember in the math, a non-homogeneous solution in which we have the solution of the homogeneous, general, the homogeneous in all solutions, the homogeneous, plus a particular solution. And then once we are able to calculate this particular solution, we calculate K1 and K2 using the initial conditions. Basically, this problem here, you already know from math. You already know. But in math, the difference is that you don't split in free and forced. You consider this problem considering the initial condition. In dynamical system, in order to go more in depth on the dynamics, in order to introduce also some application elements, this switch system, this is the switch. The switch input or system, why not? In order to physically to analyze a little bit more in depth 0 minus and 0 plus, I will do it. Of course, we consider very often this free and forced answer instead of homogeneous and not homogeneous. For linear system, this approach is valid for linear system. Do you remember I told you because I have to sum the free answer to the fourth answer because we apply the superposition principle in which we have two causes. The initial conditions as a cause, the condition at the beginning as a possible input, internal input, and the external input, but considering the internal input 0. The solution is the sum of both, no? U forced plus U free when we calculate it separately. But that's I told you many times. Okay, look, what about X tilde? The last time we concluded here. Look at this. Why I am considering this function here? I don't remember if I probably yes. No, I calculated for you in a possible solution considering just a constant input. The constant means A0 sigma t. I think I did. I think I did, but it could be that later to do another exercise I will do again. If you try to do sigma A0 multiply sigma t, we will do again an exercise. We will see an easy exercise on this one. We will see that we don't have solution. The reason is mathematically I can do another exercise later, but practically, from physical point of view, um, the particular solution reflects the characteristic of, at least the characteristic of the input for different reasons. Last time I told you, but I will come back another exercise today. This means, this means at least, we can assume that this could be an XC. In some books you can find you see fourth tilde, no? But anyway, U tilde is okay. If you don't like, so you can put UC tilde fourths, but it's okay also. The reason is in a linear system, the output reflects uh, at least I will tell you now what is meaning. The structure of the input. It could be, nevertheless, for particular system, that is not enough. This particular solution, because it could be that we need a system and a signal of the second order or third order, depends of the structure of the differential equation. But in any case, we need at least an UC, the possible forced or particular solution. In this case, we can see also permanent solution, because these two parts is going to zero if t is going to infinite. The reason is that we have this reflection from in the output from the signal which you have in the input. Now, it could happen that nevertheless we can have a polynomial expression. Again, we have a polynomial expression here, and we have a polynomial expression here. But this I told you also. But it could happen that we need also a higher polynomial. Let me try with this hypothesis. We will realize, I told you, I think, I remember now. We will realize during the calculation if this is enough or not. Look, as always, derivative of this function here. Now here, please pay attention. The derivative of this function is the derivative of this, let me say, polynomial part, multiply this, plus the derivative of this function here, multiply the polynomial, right? This means the derivative of this is a1, assuming that a0, a1 is constant, because I am assuming that the solution is basically a polynomial like this. But I don't know the constants which characterize the polynomial. Because of course, if I go in, let me say, if I feed the circuit with this voltage here, this voltage here means that the voltage increases over time. I don't know exactly which kind of function we will have steady state. You remember the concept of steady state, when the rest of the, let me say, output of the solution is going to zero. Because of course, the system, let me say, manipulates, let me say, so changes the input through the system. Just intuitive idea. Again, mathematically, we can proceed without any consideration. Assuming this, we have this expression here. The derivative of this is this one, assuming two constants. Now, please pay attention here. It is extremely important. I will come back on this topic during the next lectures. The derivative of sigma we assume to exist. We assume to be as a function delta. I don't know if you heard about delta of Dirac. I will tell you a lot about this. This means delta of t is the derivative of sigma with respect to the time. And let me shortly, from this consideration, characterize this a little bit better. One second. Let me characterize this. I will come back on this. No, now just to go ahead with the solution. In the meantime, I would like to introduce this concept, which is engineering field. This concept or the concepts. You remember I told you 0 minus 0 plus. In my opinion, are extremely important. Dirac was an engineer, was not a mathematician in the sense. Yeah, this means just to excuse me, just to understand a bit better, understand better. Of course, in some mathematical books you can find something more precise, but anyway, we are not to learn math, but we're starting from math. Uh, Typically, this is, let me say, correct, but you can find also in books something like that. Because until, let me say, 0 minus, this is the integral, uh, 0. We can see uh, exactly this. This means, let me write again this for you. So let me, we will come back to the circuit. Let me copy again. So we have everything here. I don't know if you remember, this is easy, no? From I don't know if you remember this. The integral of the derivative, no, it's the primitive, which is inside, calculated at t3. No, this is, I don't need to explain. As I told you, a time infinity 0. This means, let me write, so we will see the utility of this a little bit later. No? This is equivalent to this one, or another point of view. Yeah, this means delta is the function. Let me say once if time equals 0, 0 otherwise. This is a strange function. No? Let me see if I have I need another color to write better. Let me see if I have. I come back. Huh? Yeah, it could be. I hope that I can write with the It doesn't, I don't have, let me see if I find another one. No, I didn't find a red. Let me see. It is difficult also to represent with another color. Could be, excuse me, delta. Yeah, with the red color should be better, but it's a real strange function. Look at this. Okay. Uh, yeah, this means if I am considering now uh, again this between, excuse me, plus, clear, is equal 1, no? Because if you calculate this integral between minus infinite to infinite, for the same reason, at minus infinite is 0, a plus infinite is 1. We will see now a little bit the meaning of this strange, let me enumerate. I will scan again and I will put all together. I think this is the page number 6 today, or yeah, 4A. Something like that. I will put it in my study, but we will insist again on this concept because in our engineering context or dynamical system is important. And here I put it just here to justify that the derivative of sigma equal delta. Now we have a very difficult concept. But then we come back. No, we come back just to go ahead with the exercise. You see tilde dot dot is the derivative of this. We need this to put here to remember the method. No? As in math, you need this to put here. Look, now the derivative of this is a1 multiplied delta. I clarified a little bit that the derivative of sigma equal delta. I will explain very well. I have a couple of slides in a lecture for another course, which I will show you. It could be also today. We will see. But in this context, we will come back again. Look, here the problem is now here, no? Because the derivative of this part here is easy, as before, no? As before. This is 0, the derivative of this, the derivative of a1 multiplied t. Again, a0, b0 is written here. They are constant. This means a1 multiplied in delta, clear. Now, the problem is, what is the derivative of delta? This is a concept extremely difficult to be understood. I will try in the future. At this moment, I will tell you just that the derivative of delta is not in a function, it's in a distribution. I will tell you now a little bit what this is. But let me indicate at this moment this form. Then we will come back on this. Formally this one. Assuming that I don't know exactly what is, because I have to characterize the derivative. Why I have to characterize? Because also the derivative of sigma is a little bit strange. Because you remember we learned that the derivative in the standard form, the derivative of non-continuous function does not exist. I can do the derivative left, I can do the derivative right, with respect to the non-continuous, let me say, of the point in which we have this discontinuity. You remember, I cannot do the derivative here. Of course, this way to think is an extended way to interpret the derivative. The derivative. We will see the effectiveness of this interpretation in our field, in the dynamical system. Here is more difficult. What is the derivative of this? Here is more difficult because of course, we can say the derivative left is 0, the derivative right is 0, but what happens here is more difficult to be understood than this one. Here is also not easy, but I will try to show you what is the meaning here. Here, it's really strange because the function is defined, if it's defined, at 0, and the value is infinite. Oh, excuse me, I made mistakes. One in yeah, one in discrete form. Yeah. It's infinite, excuse me. Makes a little bit sense, no? If you think a little bit to approximate this function, we then continue. I show you now with the presentation. Excuse me, I made a mistake here. Otherwise, cannot be in the sense everything which I told you until now, plus infinite, but characterized by the integral equal 1. I will show you again this. I will show you with the graphical interpretation. If you okay. Let me indicate so. Now, as I told you, this is not defined, in particular at t equals 0. Why that? Because outside 0, we can understand. The derivative here, the derivative here is 0. Here is not clear what happens. Let me consider now, starting from t larger than 0. From t larger than 0, we can say so. Also graphically, we will see a little bit later what is the meaning. But of course, what happens between 0 minus and 0 plus remains, as I told you, in general, something to be analyzed. This means we will see later. But at this moment, considering that at 0 minus, between 0 minus and 0 plus, no particular thing happens. I mean, you see at 0 minus equal you see at 0 plus. This is the constant. This means from t larger than 0, we have, as I told you, 0. Let me see how I can let me see, because I don't understand now. Where this come from now? Let me see. Yeah, of course, it's clear. So this I told you is 0. I didn't see this. We know that for t larger than 0, this is also 0. No? This is also 0. This means imply this again. This means if I plug in now this this and this here, I will obtain 0 UC tilde dot dot. This part here is basically this here, because this is 0, no? And this part here is this, equal T multiply sigma. As I told you last time, that's easy to calculate it. Now, where is the page? Don't find it. I lost. Oh no. I found it. No? Yeah. Page number 5. Why this is the solution? Is the solution because if you look at this expression here, we have that A1 must be 1 if you compare, because this element with T, we did many times this exercise. With element with T multiply sigma, it's just here. This means A1 necessarily must be 1. And then the other condition is exactly this A0 plus, excuse me, A1 plus A0 equals 0. Otherwise, I cannot satisfy this condition here. This is an identity. I don't know if you remember in math. When it happens that the left part equals the right one. This is the unique solution which we have. No? In any case, A1 equal 1 because it's the unique element left and right depending, multiply by T, this part here and this here, A1 equal 1. But also, this must be 0 plus this must be 0. This means A0 plus 1 must be 0 because here we don't have any constant multiply sigma. This means from these two conditions, we have this one. This means A1 equal A0 equals minus 1. And A1 equal 1 is the solution. If I now plug in my initial hypothesis, I have a solution. You remember in math, we learned that the linear differential equations have one solution. This means this is the permanent solution. This is the unique permanent solution which I will add to this general part, let me say. And then I have to calculate K1 and K2 using the initial conditions. This is, you are able to do that. No? Basically, you have to consider this at time 0, and you do the derivative, and you consider also at time 0 is 0, no? For the force. This, I put this 0, I calculate what happens on the right part at time 0. Then I have to do the derivative. I didn't do for you, but you can do at home, as we did always. And then we do the derivative, and again you calculate the derivative at time 0, which is 0, because in the fourth situation. And then we have two equations into unknown. The unknown are K1 and K2. Few words about, we come back on this, about this derivative of E. This is not a function, it's a distribution, which is defined. So we come back on this. It's extremely abstract, but we come back on this. The integral of f of t multiply the derivative of delta, let me indicate so, equals minus f derivative calculated at 0. This means the derivative of this you remember that this is math, no? I eliminate the integral. let me say so, the second derivative of f calculated at 0. This is quite abstract and a possible interpretation, but can help to a little bit later we will see to understand what happened at 0. What happened at 0? This means this in this system here, this condition here holds in this system here, consider this input, of course, this condition here holds also at time 0. What is the meaning? Let me show you. We had this problem. You see tilde. No, it is, excuse me. We have A0 plus A1t exactly. In our case, this is our f of t, multiply the derivative of this. This was the open problem. No? What happens here for t larger than 0 is clear from the definition of delta. I will come back again on this topic, extremely difficult to be understood. But with this possible definition of this delta derivative, which is not a function, please pay attention, is the distribution. I will come back a little bit, but not much because this is more mathematical aspect. But let me analyze this a little bit to more in depth. To be more in depth. This is our f of t, and here we have the in this notation. Sometimes in the book we can find the derivative with respect to the time with dot or apostrophe. No? But you can use dot apostrophe. You can use explicitly this. If you look at this definition, or the definition is one, but this expression here k comes automatically, in which we have the derivative, the second derivative of this calculated at time 0, we have 0. Because the derivative of this first derivative is a1, the second derivative is 0 for each time. This means also at time t equals 0. This means that this expression here says exactly what happened at 0, no? What happens at 0 in our case? I told you here, derivative. In such a situation, calculate it at 0. In such a situation, of course. Let me, this means if this is the function f of t, which we assume as an output, no, of our system. Uh, Somehow, this means, you remember, this was our hypothesis. According to what I told you until now, this is again, this remain as f of t. As I told you before, it's zero, not only for t larger than zero, as I told you before, but also at time zero. Let me write. Calculate at zero, yeah, lo Francesco. Let me write explicitly, not only for t larger than zero, but a little bit strange, but this means calculated zero. But also for t equals zero. Yeah, I will come back on this because it's a little bit difficult, but we will see also with slides a little bit better delta. When we able to understand delta, we will come back on this concept here. Okay. Let me think if I forgot to say something. Otherwise, we will try to do another exercise because before go ahead with another topic. I think it's okay. Yeah? Again, if this is the structure of the solution, which it seems to be for the system, for the given system, yeah, we have exactly that it zero, the second derivative, not only for t larger than zero, but also for t equals zero. Okay, this is related to this, no? Okay. Let me see what I can add. Mm. I don't think so that at this moment I think I told you everything concerning what I can told you in accordance with the knowledge which we have. Uh, mm, yeah, a little bit we can understand how again this concept of 0 minus and 0 plus. Let me now at least mathematically tell you about this. This is the page 5, the page 5a. Let me now if at time 0 is equal to 0. Now let me consider again this here. We have that this expression, if I copy from here, let me copy for you. I copy. Exactly. Let me see what I would like to told you now. But I think I already told you this. I don't think that I have to repeat. Let me see again. I don't think so. It's necessary to. No, if you want, I can look. Yeah. Do you remember this? Uh, no, I can tell you. In general, this was, no? Of course, if you look at the initial condition, which implies also this, because this is the general, no? This is the particular. This means, excuse me, now we have this one. We have this one. If you uh, consider the differential equation, which I copied here, excuse me, I didn't find. This was the general one. No? This means it works also for a particular. You remember this. We can consider also the particular. No? This is valid in general. This is valid also for this. Now, what happens at time 0? Because of this presence here. But this it's 0. This it's 0. This implied 0. No? Okay. And this could be done, as I told you, also for in general. No? from here. Times 0. This is trivial. I mean, if I times 0, this is 0. If I times 0, this is 0. This is 0 in any case. This in general is also 0. This imply, if you consider what I told you here with this sigma, which makes the difference between 0 minus and 0 plus, that we can say that between 0 minus and 0 plus, yeah, we don't have any changes in the initial conditions. We have a continuity. No? In general. I will come back on this topic because this is just an introduction. We concluded here saying that once we have UC free of t and UC forced, I didn't calculate until the end this, but we did many times in the last weeks. UC in general equals UC free plus UC forced. Free. No? Okay, we take a rest a little bit. We will come back and we continue the lecture. Let me say 50 minutes. So we recover a little bit the time which we have to recover. 10 o'clock, we will come back for the next step, let me say, or the next part. Thank you. Okay, now we will see more in depth a little bit this concept of 0 minus and 0 plus, and then I think today it is good to tell you with some slides about sigma and delta. I will left at this moment this derivative of delta, which is a little bit more complicated, but I will come back probably next week in these 2 hours which we have. And then I have to really go ahead with the program in June, in which we will see a little bit the dynamics of controlled systems. Nevertheless, dynamics. Now, a little bit more in depth, 0 minus and 0 plus. I consider now, I show you, I prepared for you exactly now very quickly an example which at the beginning I would like to say, given really in a feeling that what was at 0 minus, why I am speaking what was, because this is the past. 0 minus sum up everything which happened in the dynamics or in the system. Let me say now we will consider in a system without dynamics, but anyway, in a system without dynamics, it seems to be a contradiction in the course entitled dynamical systems, but allows to understand a little bit better the dynamical systems in a sense. Everything which is summarized in a time 0 minus, and then something happens. I mean, we have the switch, we try to control starting from this point, we try to observe, we will see in some master courses, or if you come to the course next semester on Kalman filter, we will see together what an observer is. Starting from 0, this means 0 minus 0 plus could be also something interesting, no, in our case. Let me switch on the lateral camera. I prepared for you very quickly an example in 2 minutes. Even though the example is easy, I hope no mistakes, but eventually we will correct together. Let me restart with the page number 1. Look, we have this kind of system. Probably you have seen in electrotechnic, of course. Of course, we have seen. C1 equal 2, C2 equal 1. Excuse me, C1 equal 1, C2 equal 1. But you can put whatever you want. Now we will see also symbolic the meaning. I give you also the initial value, excuse me, here minus, of the voltage, but please pay attention, at time 0 minus, both. Basically, before closing the switch, the switch is going to be closed at t equals 0. At t 0 minus, we are still open. This means that t equals 0 is going to be closed. This means, as I told you, summarize what happens in this part of the circuit, which I didn't indicate. At the end, it doesn't matter what was here, was 10 volts. Here at the end means until 0 minus. Somehow, no, I didn't do anything, or I did something, but at time 0 minus is 0. Question. Calculate VC1 at time 0 plus, which is equal VC2 at time 0 plus. You know from this concept of parallel. Parallel. I don't want to go in depth on parallel, but you know better than me. How we can solve this? Again, we have something, everything, this is given, fixed, assuming that doesn't change. We have the voltage at time 0 minus for C1, we have the voltage at time 0 minus for C2. The question is, what is the voltage at time 0 plus? I don't need to specify, which one because they are parallel. We know that this is in a structural condition. Probably in electrotechnic, you discuss where this comes from. But this is basically is an equation which came from experimental, is in principle somehow from experimental considerations. I don't want to now to go in depth on this, but you know that this is valid. This means in our case that the load equals in all case C multiply V. But what is basically the meaning, in particular, how we can apply this equation here in our context? Yeah, look what I wrote here. I wrote at the end that the load at time 0 minus equals the load at time 0 plus. This is the principle. The principle is the conservation of the load. I mean, in this system here, the load which we have before closing the switch is equal to the load which we have after the switch. If I consider also the capacitance of the capacitor too, because we have just this load, we will be distributed in the new configuration. This means in this kind of system, of course, in this kind of system, what we have before closing the switching at time 0 minus will be equals what we have after closing the switch, because of course it's in the principle, it's intuitive to understand. Let me say the system C1, C2 characterizes by C1, C2 is in a closed system somehow. No? This means Q 0 minus equal Q 0 plus is something which can be assumed valid in accordance with the conservation of the load for, let me say, closed system in the sense which I clarified. Now, C1 multiply VC1 at time 0 minus is our load before, in accordance to this law, before closing. And what is Q0 plus? This means after closing the switch, excuse me. Is C1 plus C2 in accordance with what we know from electrotechnics. I don't go in depth on this. But of course, it could go in depth is easy because here we have this after close, this load plus this load. It's written here. C1 multiply VC1 0 plus is the load here after. And the load here after is C2 multiply VC, excuse me, here is, yeah. It is better to indicate not VC1, but VC, yeah, it's not wrong though. Sometimes in some books you can find VCX, but I would like to say so, because we have, it's correct because at time 0 plus, we have exactly what I told you before. In some books, nevertheless, they say VCX, but it's the unknown is given from here, because this is the question. But this now is easy to calculate VC1 at time 0 plus. Please pay attention. I like this notation because this is unknown because of 0 plus. Because 0 plus is unknown. In some books, they write 0 VC1x until that, but this is, I like better. It's ready. This is the solution. C1 divided C1 plus C2, multiply this, which is known. Which is known here. 1 divided 2 in accordance with our value, but could be any kind of value for C1 and C2. Multiply this. If you want, I can write exactly, it's fine. Because this was 10. No? Now, let me draw directly what happens. VC1 is starting from 10 until 10, and let me say, until 0, at 0 minus 1 is 10. That is not exactly, it is correct, it's correct if I think about this. No? But of course, it could be that here I have another circuit. This means it could be that I have an function, but at time 0 minus is 10 volts. Is 10 volts. Here, in accordance to this picture, it seems to be 10 constant. And then, look, please pay attention. Between 0 minus and 0 plus, we have a function which is not constant, excuse me, which is not continuous, because at time 0, this means between 0 minus and 0 plus, time 0 is between, we change from 10 to 5. In accordance with what I told you here, what I calculated here. Now, what happens VC2? At the beginning, we had 0. You remember? The beginning, let me say 0 minus. What we have as a 0 plus, because of this condition, this is the parallel. We spring, let me say, we spring at 5. This means at time equals 0, we spring from 0 to 5. 0 is again between 0 minus and 0 plus. And then we will remain in accordance with our scheme. Here is the situation. Excuse me, I don't have a red color to write. With this easy example, which is not a dynamical system, now we will consider a dynamical system. At least we have a better feeling that it could happen. Now, of course, this is in a particular case, but it could happen. We will see also in the dynamical system, even though it's not so, let me say, it's not so common that we spring, but it could happen, and we will see together. But in general, we can see that not necessarily what we have before starting with our simulations, let me say so, before starting with our control, before starting with our observation, is equal when we start the observation. This is an example, even though not dynamic, in which we can see, in accordance with what we learned in electrotechnique, that to think about 0 minus and 0 plus in general could have a meaning. No? Okay, this I will scan again everything and I will upload. No? At this moment, yeah, the material in my study is updated. But it could be that sometimes I change and improve. I will scan again. No problem to scan. Now, we have a better feeling. 0 minus, 0 plus. Already the definition was difficult, probably because you didn't hear this in electrotechnical. But in dynamical systems, make more sense. We will see now again. Even though in electrotechnical, such kind of example could be considered, but of course, isn't an example that is a little bit artificial. Because if you remember electrotechnique, or at least in electrotechnique for engineering, we have always here a resistance. We have always here a resistance, which characterize the losses for both capacitors. If I have a resistance, change everything. Let me show you exactly this example. Page 2. Exactly this example. Let me see. This example, but in this form, because it's more usual. But you can extend also with 2 capacitors. I think we have already seen this example, or something. No, I don't think so. I don't remember if I. You input, you in. Yeah, could be 0, could be 1. I mean, I can consider the free answer. Let me say position 0. No? I don't know if this makes sense. Something like that. Switch equals 0, something like that. Which equal 1. I don't know the notation because I use basically different notation. Okay, let me do a really easy example. R equal 1, C equal 1. Extremely easy. The value does not matter, no? It's clear. Yeah, this is everything. Let me consider V C at time 0 minus. We start to introduce this concept again, because probably I introduce a little bit in very hard form when I consider directly the system of second order. But again, at that, when I introduced this, the idea was to show you the solutions, even though I already told you about the system of second order. But now let me come back again in an easy example, but go in depth on this 0 minus. I don't know, any value. 12? No, 5. Let me say 5. Typical. So. Exactly. Let me now consider, this is the initial condition, external input, U input of T equal sigma of T. Interesting now. Sigma is clear because we have nevertheless a sigma. This means theoretically I have to write the value which is 1 if this is If I don't put anything before sigma, this means this is 1. But let me write so. 12 multiply sigma of t. This means this is 12. It's not exactly, let me write u, otherwise it's confused. This is u, and u input. Now it's clear, most clear. Last time I was more precise, but now it's precise. This is u input. I don't know if it's clear. U input is 12, which u of t is equal to 12. U of t is 12, and then considering the switch, I have 12 multiply sigma. Once could be 0, once could be 1, it depends. Depends of two possible situations, if you want. We analyze the two situations, right? Let me formulate so. Or we can see let me formulate better. This is the value in general. This is the situation, first situation, which I want to analyze at the beginning for S equals 0. And then we will see another situation for S equals 0. I don't need, this is wrong. So, is for S equal 1. Let me put here 0. Okay. And then the other situation now makes sense. So we do this parallelism with the free and forced in the context of 0 minus 0 plus. Now, 5 volts. Yeah, we don't need this. We don't need this, no? Because this is related. I know, maybe. Yeah, exactly. This is related to this square one. For S equals 0, we need just this. No? Let me see if I. Basically, what is the meaning? The meaning is I would like to analyze in the context of 0 minus 0 plus, given the condition at 0 minus in both cases, but connected with the free answer and fourth answer. I don't know if it's clear what I intend. Yes, fourth, let me write. So, answer. Or response, answer, yeah. Fourth, because you have initial condition 0. But you have the input. The input is this one. I can consider the switching if you want. So I switch. I will consider the fourths. What happens when I switch? Yeah, I will consider the free. Again, when I switch in the present, S equals 0 means I am, as is strange, yeah, at t equals 0 could happen S equals 0 or S equals 1. No? Let me write so. It's difficult with the let me say right. So at t equals 0, probably it could be useful to understand what it is. Let me analyze this. What is new with respect to 2 lectures ago? This here. Before we consider directly 0, no? Most of the time we don't need to analyze this, because as I told you before, in this complex situation, but not complex in terms of 0 minus 0 plus, at t equals 0, this means in between 0 minus 0 plus, nothing happens. What is the meaning of nothing happens? So we have the continuity of the state. Please pay attention. The continuity of the state. But as I told you before, in this example, even though it's not dynamics, now we will see a dynamical system. It's not always so, but in general, it makes sense also in this case to look at 0 minus and 0 plus, because even though we will see the states remain constant, excuse me, continuous, some variables can change between 0 minus and 0 plus. Let me consider that. S equals 0, this implies at the beginning free answer. No, typically we start always with this, but not necessary answer. Okay, let me start to analyze this. This means UC of t derivative. Let me write here what UC of t is. The state, again, the energy is characterized by the electrostatic energy. Basically, we did also before. The load is close to the energy. I don't know if you remember this. Plus u c of t equals 0. Now I clarify this, but I already told you about this. No? Equal 5. Why this equation? I don't know if you remember. It's the Kirchhoff. No? We are in this position here. We are this position here. Or we close at this position here at time 0, knowing that the time minus 0 is 5 voltage. Let me write 5. This equation, I think I don't need to clarify. I already clarified this. It's the Kirchhoff balance when I close. But the information which I have is at time 0 minus, short before closing. The Kirchhoff balance, I think we don't need to do. But in any case, the voltage here. Let me say plus the voltage here equals 0. What is the voltage here? C times the derivative you see. Excuse me. Let me think. The voltage here you see. This is written here. What is the voltage here? Excuse me, let me see. Is the current multiply R. But what is the current as a function of the state? Is C time the derivative you see. But C is 1. I don't know if it's clear. I don't know if it's clear here. I already clarified this. The Kirchhoff balance. The state, excuse me for mistake before, you see this voltage plus this voltage. No? From here to here, assuming that the positive direction of the current is clockwise because of plus minus. You know better than me from electrotechnique. This means UC plus this voltage from here to here is R multiply the current. But what is the current in this context here? Is C times the derivative of UC. But C is 1, this is the balance. Okay, the new thing with respect to before is this minus. Let me see now how we can manage this. Assuming that, let me see 3, no? So this is consequent with the notation which you use until now. Because here analyzing the force, we have a 0. No? Just to analyze, the idea is to analyze 3 and force in the context considering minus and 0 minus and 0 plus. Because in electrotechnique or dynamical system, this system here, dynamical system is, as I told you, a mix between math, system theory, and control. No? This means it's not only math, which we don't have the switch S. Assuming that, you remember, UC of t equals the same consideration, k exponent up to lambda t. Do you remember this? Even though now we know that lambda is -1 here. Probably I don't need to calculate, but I do it for you because we did many times, no, how we can. But anyway, if this is invalid, we know that. No, invalid. Let me say assumption. If this is an invalid assumption, if we are able to demonstrate that this is really the structure of this solution here, this implies, let me calculate, because we don't know if we find lambda. Okay, we know because you can imagine that lambda is -1. Let me calculate, and then I do the consideration. K is a constant. I forgot to say, I don't remember. Let me write here. You remember at the beginning of the semester, I calculate everything within a general approach in which K is a polynomial, a function, not only a polynomial, it's a function. But anyway, we know that when a function, when the function collapses in a particular function within a constant. Let me do so. Now plug it in. I plug it in here. I plug in this here. You remember the exponent is never 0. I can cancel. K also cannot be 0 because of the presence of this value here. And then if I put equal 0, okay. Again, this, how possible to say UC3 equals 0 is not the solution because of this condition here, but not only 0 equals 0 is the condition which does not, nevertheless is valid, but is not constructive. Assuming that it's not 0K, this means I can cancel. Let me see what happens. You have a constructive condition, which is this one, which justify lambda equal -1, as we knew, no? You remember? Therefore, at the beginning, I told you we discussed a lot. We knew probably you did something more precise in math. But anyway, this is the solution, the structural solution, but we have to calculate K. But already from here, looking at this function, which is structurally is the solution of this equation here. Um, Probably, let me see if I can improve a little bit this. Because so is not really exactly what I want to. Let me see. One second. It could be that should be clarified a little bit better the concept. But it's good, good. We can. I think we can go ahead in this form. Yeah. Let me. Yeah, I think so. This means of this function here. Yeah, this means now k, we know that is 5. Let me now calculate this. Exponent minus 0. This means k equals 5. At the end, we have uc free of t equals 5 exponentials minus t. This means we have 5 and then something like that. Let me see if I can improve. 1 thing probably, yeah, I think it could be. Let me see 1 second again. Yeah. Okay. I think I didn't get anything, even though I thinking if I can improve a little bit the explanation. Um, I don't think so. This will be. I think we can we can proceed. Uh, I think in this form. Hmm. Interesting to look at at the current. The current is basically, I don't know if you remember, E free of t equal c time u c of free derivative. And if you do now these calculations in this form for this, what happens? What happens is this x free of t is, of course, to be precise, is this for t larger than zero. And as we know, x free of t equals 5 for t less than 0 or equal 0, because we have seen that at time 0 we have a 5 as before. Basically, this is the old solution. This means if I do the derivative of this expression in terms of current, I have the derivative of this is minus 5 exponential up to minus 2 and 0. Yeah, I forgot to write, but I told you basically which is here. Now we can understand a little bit better what happens, because here we have 0 for the current E free, and then starting from minus 5 ampere, we have this. Let me see if I can improve a little bit. We can see that we have the difference between 0 plus and 0 minus in term of current. Let me see if I can improve a little bit. Explanation and so on. The state is continuous, but not the current. The current is not the state. Let me think if I can improve. I don't think so. This could be also quite clear, I hope. Um, would be would be improved probably. Let me see 1 second. But I would like to remain in this format at this moment, as I think is comprehensible. Nevertheless, it's comprehensible. Um, I think so. You have to say probably a little bit better. Okay, let me now analyze the second case, this fourth answer. Yeah, free answer. This one, if I want to consider also this is the free answer in terms of state, this is the free answer in terms of another value. Let me so analyze the fourth answer. Yeah, the fourth answer consists of this. Hmm. Uh, to be precise, but we don't need in this sense. Here we have an input which is zero, no? But I did input because of this. I don't know if this is clear what I intend. You input here is zero. I did input because in the sense here. What is here is zero multiply sigma, if you want. If you want, I write. In the fourth answer, you input, including them, is zero multiply sigma. Okay. Fourth answer, again, now it's not zero multiply sigma, but 12, and here is zero instead of 5. Okay, this means that UC of T fourth is K1 and K2 before I put K. Now we distinguish. You can put the KF, K3, K4. If you want, I can do, but it's not necessary. Plus, now what? The constant, let me say A0, which multiply sigma of t, because you remember, this function here reflects this function here. Before was 0 multiply sigma, therefore I didn't put it. Now it's 12, but I don't know if we will, at the end we will 12. It could be. It could be another value. We have seen, depends of the structure of the system and on the value also of the system. The thing which we have to consider here as before is, do you remember before? Let me show you what I intend now, because we have to be a little bit I think this is we can go ahead also. in this form. Huh? We have to calculate the solution of this. Basically, A0. To be precise, in this form, even though we don't use, we have also here sigma, because the forced starting also this part for sigma. Let me now consider this. This is our xc force of the without a tilde. Remember this. Sometimes with force, we can put it, but tilde. Derivative is A0 multiplied delta. You remember this? Yeah, let me see if I can improve. Yeah, let me look. This means if I plug in here, I have, as before, this function here. Now I copy it better. No? This is the UC tilde forced derivative plus A0 sigma of t, which is UC forced tilde equal 12 sigma. This means, as I told you before, for t larger than 0, A0 in our case is 12. That's E0, and A0 because we have R equal 1 and C equal 1. In our particular case, in this particular initial differential equation, we have A0 equal 0. For t larger, let me say, than 0, we have to recall that we are considering for t, let me say, larger than 0. Let me, this is the name, page number 3. Which means for UC at times yeah 0 plus, because this is valid at time 0 plus. We calculated do you remember, for t larger than 0, we have 0, because 0 plus is equal 0 minus in this sense, as I told you before. This implies k plus 12, because this is 1. This implies k equals minus 12. Let me write definitively solution, and then we will discuss it a bit. Mhm. Yeah. Sigma, I forgot here, sigma, because C force is characterized by the sigma, which is not multiplied by 0. Let me see if I forgot to say something here. I think so. I don't think so. This one. Let me see if I forgot to say, but it's verify a bit better, probably. Mm. Um, Let me tell you one thing, probably, but I don't think so it's necessary now. Why this equation holds also at time equals 0? I told you before, let me show you again. So we have considering, remember the definition. I will show you again tau. No? You can write also t is not a big problem. This was this. I show you. I don't know if I told you this. You see, yeah, I told you in terms of the derivative. Let me see. Please. When I define the 1 second, I don't find that there's a this the new slide. I didn't tell you about this. This property I didn't, or at least not directly. Let me see, I didn't tell you. Yeah, this is another, let me say, yeah, characteristic of the delta function. It's quite similar to the distribution. We have a seen for the distribution multiplied by, if the multiplication is by the derivative, we have here minus the derivative of this. You remember this. Now the minus is a little bit complicated this moment to why in the derivatives is minus, but at this moment, believe me, if we have this possibility, this means the derivative of this as before is equals the derivative of f with respect to time, calculate as 0, or you can put also here 0. This justify why also this equation here is valid also at time 0, because this product is 0. Assuming that A is a constant, assuming that existence is 0 constant. But exists, because we calculate it. Basically, assuming that is the constant, this is 0, and then we calculate the constant. This is a little bit this mathematical analysis, procedure analysis, you can say. Let me see if I can improve a little bit. Everything. Yeah, I forgot to say sigma. This is nice, this property. I will come back just now with some slides now on this. Let me see if I can improve something here. If you want, also here, if you write phi larger than equal 0, you can cancel this, and you can write, basically, this is exactly the definition of sigma. Here remains O, but here you can write x minus t multiply sigma out. Because this is exactly the definition of sigma. Remember, it's 1 for t larger than 0. This means at the end, uc of t is equals u free of t plus u forced. Then we will see what this means. 5 exponential minus t sigma plus 12, which multiply 1 minus exponent minus t sigma. This is enough to write. So you can also do some calculations if you want. No? And here, 5 t less than 0. Yeah, you can do the calculations. I think it's almost everything. Now we will go in depth on delta sigma with some slides, and I have more slides for this distribution of the derivative of delta, but it could be that I have to look for this slide because it's for another course, a master, the distribution. It could be that I will tell you next time. Now I will tell you something about delta sigma. So it's basically important to analyze this. And then we conclude for today. Let me see. Nothing, some something to be improved. I don't think so, nevertheless. Yeah. I think we can go ahead with the presentation. An exercise to do at home. Let me see. But let me present. It could be that later I will have an exercise for you. Let me find the material. Excuse me, I have to answer 1 minute. I come back now. Okay, let me now conclude the topic of today, showing you a little bit more in depth sigma and delta. And then next time, I would like to try to very shortly to speak about the distributions, or the distribution which we introduced today, even though it's not exactly, let me say, the topic. As I told you, this concept of sigma, delta, and the derivative of delta as a distribution is a topic of another course, but nevertheless, I have something also in the dynamical system we can see in the context of Laplace transform and simulation. Let me say Laplace transform. Let me tell you shortly about this Laplace transform, even though about Laplace transform I will continue next week. No? I hope also together with, I don't know, the distribution, but it's a little bit more complicated. A few words about the Laplace transform, and then we will start directly with the delta. No? Look at this. Probably you know from math what is the Laplace transform. It's defined in this form here. F of t, which multiply the exponential function here, e is the exponential function. This is up to st in dt. What is this? Isn't a parametric integral which transform everything which is in time in S domain, in which S, we can see here, is the complex variable. You remember the imaginary part plus, better to say plus minus j omega, and complex value. About the Laplace, I will come back, let me see, next week a little bit more in depth. The goal now is to, because I told you about the delta and the sigma, let me reconsider what I told you with this slide. Delta is the impulse. We can see the meaning of this nomenclature or definition of the Dirac impulse from this part of the definition. Let me say infinite at t equals 0, 0 otherwise. Do you remember? Let me show you how I represented before. Let me find, yeah. Because in one small, infinite small time is plus infinite. Look at this. Exactly what I told you. At time equals 0, 0 otherwise. For t different to 0. And this, you remember this? This came from what I told you before. And in fact, if you come back to the lecture, there was all this information in the definition exactly what I told you. Very important, but we will see next week, this impulse response. But somehow you can understand what I'm thinking. We will see next week a little bit, because today we have seen sigma response, step response. In input, we have steps, again, to understand. And the delta we will see next week. Let me show what I intend with when I say sigma response or step response. Yeah. So here we have the step response, but the step is 0. Therefore, we have a free answer. Here is the step with amplitude 12. Basically, I put this signal in input. Which this is 12. 12, oh, yeah, 12 sigma. I put, and I would like to see what is the output, and we calculate the output. Sigma response or step response. This is the step in input. Input. We will see next week a little bit also the delta. I introduced the delta in the context of sigma, which is a little bit more complicated, but extremely important. With the delta, we obtain an impulse response. But the goal now of these 10 minutes, of 5 minutes, to tell you a little bit more about this delta. So it's also an introduction of next week, in which I will introduce the input, unit impulse. Practical example in order to understand intuitively what is this abstract solution, signal, which generates an abstract solution of a differential equation. And next week we will see also a little bit, but very shortly, this distribution. Look at this. Three real impulses. This is an impulse. This is another impulse. This is another impulse. All these impulses are characterized by integral equal 1. I don't know if you see that these 3 signals are 3 impulses. Why that? The reason is close, let me say, the real impulse, close to 0, they are not 0 anymore. No, we can see here 0, 0. Let me say generally, roughly speaking, close to 0, this is 1. Also here, more closer, more close to 0 here, closer to 0 is the amplitude 3. Here, even more close to 0, the amplitude is 10. But the integral of all these impulses, real impulses, is 1. Look, 1, the amplitude, excuse me, 1, the amplitude, 1, the amplitude, multiply, this means this level multiply this interval here. The interval is 1, no? Between minus 0,1 and 0,1, the interval is 1. Multiply 1 is 1, the integral is 1. Look here, the amplitude is 3, which multiply 2 times 1 divided 6. This means 3 multiply 1 divided 3. Again, 1. Look here, the same concept. The amplitude is 10 of this signal here, and it takes 2 times 1 divided 20. This means 1 divided 10. This means 10 multiplied 1 divided 10, the integral is 1. This means somehow they have integral 1. This is the most important characteristic of delta, because this is the real characteristic. Now, if you reduce this interval here, you realize an amplitude higher, we can nevertheless have impulses with integral 1, which is the most important characteristic, which takes in time shorter and shorter durations. Ideally, we can reduce to infinite small duration and infinite large amplitude. This is the concept of the delta. Now, let me analyze again, together with you, this condition, because, or this relation, because we started from this in order to go more in depth on this concept. The derivative of sigma equals delta. And then we completed everything which we discussed in this slide. Yeah, 3 minutes, I am ready for today. No? Now, again, I told you about that. No? Do you remember? Step, as is clear, probably you have seen also in the context of electrotechnics. Do you remember this? I told you this, consider at the beginning this one, but this is we can do in both directions, because we know that the integral is the let me say inverse in some sense of the derivative and vice versa. This means you can start from here to obtain here, as we did in the lecture, or start from here to obtain this. If you do the derivative of this, in fact, we have this one. But if you do the integral of this, we have this one. The integral between minus infinite tau. Exactly what I told you. If this equation is, if you look again on the slide, is exactly so. The definition of the definition of this one, the graphical representation of this here. This is switch in our case. Look again. This is the last slide of today, 1 minute, and I'm ready. And next week we will go in depth. A little bit better than today, because we have more knowledge. Look, I put just these 2 cases, but you can do the same also here. No problems. Look, delta is the derivative of sigma with respect to t. How we can graphically justify this equation here, or this equation here, in accordance with this practical interpretation of this definition. Yeah, look at this red color graph. If you consider now this distance, let me see. Let me see how I can express better. But this distance divided this distance, which is the derivative, is 1. This red position is 1, divided this duration is 1. This means 1 divided this 1 is 1. But basically, it's the derivative of the red. Look here. Here is better to see, because here basically we have the same point, the maximal point of the red with the maximal point of the blue structure. Look here. This distance, 1, divided this instance, which is 1 divided 3. 1 divided 3, which is the derivative of this red color line. Because in a linear structure, it's 3. Exactly our sigma, or at least here is infinite, it's clear. I mean, starting from this, let me see here. Starting from this, we have, starting from the blue structure with its, let me say, characteristics, amplitude, which is not infinite, but is 3, and integral, which is 1, the most important characteristic because remains everywhere. I can build here the delta, excuse me, the sigma function, and I can see that this, the derivative of this sigma function, so defined, or so graphed, is equal sigma. Or at least the amplitude of sigma, the derivative of delta, excuse me, this real delta, the derivative of this sigma equals the amplitude of this. I don't know if you see this. At least the amplitude. Here you can do the same. If you consider the same, let me say, the same step, starting from here until 1 at point t divided 20, we have 1 divided 1 divided 20. This means in terms of amplitude, the derivative of this sigma is exactly this real delta. Now, try to think to reduce. We have exactly this expression here, which the derivative of sigma, exactly this one, is equal to the amplitude of delta. What is the meaning, amplitude of delta? This part of the definition. Really, we have some values. We have seen case 1, case 2, case 3, even though I didn't put. But of course, if you reduce, we have exactly this part here. Let me see if I forgot to say something. I don't think so, intuitively, of course. And here we have seen today the step answer. No? But we will come back next week with the different examples. Let me see if I forgot to say something here. But I don't think so. Of course, to conclude, nevertheless, we verified also this concept here, no? Between minus infinity and plus infinity is clear. This is 1 if you think about the picture which I told you, because outside of the interval are 0. And here the integral bit is -1 and plus, excuse me, minus infinite is plus infinite is also 1, because this it takes, we remains at 1. Or at least to tend to 1. You see. It's 1. Because mm, you have an error here, excuse me. Yeah, excuse me for the error. No? Stupid. I told you before, but then I made mistakes. Excuse me. I tell you. Yeah, excuse me this. Yeah, now it's correct. From here. Excuse me for the error. No? Yeah, it is definitively no, from here. Excuse me. I told you, but I forgot to say. Okay, to write. I forgot. I told you, but I forgot to write. In any case, we will see. We can understand better again this discussion next week with some exercises, and then we will go ahead also with the Laplace transform in the context of the analysis of this dynamics. But before going ahead with the Laplace transform, which is the lecture number 5, we'll insist a little bit on this delta, sigma, and so on. No? Please pay attention that this last was originally wrong, even though was correct here. And then here I told you, when I told you to remember the integral of this is sigma, calculated minus infinite 0, calculated plus infinite is 1. Do you remember this? But then I didn't write correctly, but now I corrected it, but it was correct here. Okay, we conclude this part. We will go in depth next week in time. I was thinking about to tell you about the derivative of delta with exercise, and then we will attack the same problems, or we will see the Laplace transform of this analysis, the dynamical analysis. And then the course go ahead with the dynamics of the controlled system. We speak about a controller. Do you remember? Mix between mathematics, system theory, and dynamical systems. I will tell you something about a linear controller for linear systems. And then we will see a little bit very shortly nonlinear controllers, one kind, for linear and nonlinear systems. We have nevertheless 7 lectures, something like that. We will see next week. And thank you for your attention today.